Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin. Find the tangent line to the implicitly defined curve 2y cubed plus 5xy squared plus 3x equals 10 at 1, 1. Okay, so now there's a key word here that jumps out. There's actually a couple key words, but one is implicit. So we're like, oh, this is an implicit function. And so we say, I bet you we're going to have to do something with implicit differentiation. So we sit here and say, okay, so implicit differentiation, remember, that means that we're going to think of y as being a function of x. So whenever we see the word implicit, we have that thought. We also, of course, see another key phrase, namely tangent line. Okay, good. Well, what do you need to make a line? Two things. Point, slope. Good news? Point. All right, we're halfway there. So we need slope. How do we get slope? Well, still good news. There's a way, the derivative. So we're going to take a derivative, and we're going to find our slope. So remember, how do we do it? We have our thought. We're going to take the derivative of this expression here, both sides, with respect to x. And whenever we take a derivative involving y, we're going to say, well, hey, y is a function of x. So we're using the chain rule. All right, so here we go. We'll write the expression down one more time, just for a quick reference. 2y cubed plus 5xy squared plus 3x equals 10. And here we go. Partial x. Now you might say, 0, right? Because there's no x. But there is. Y is a function of x. That's why you have to think chain rule. So 3 comes down. 2 times 3, 6. Y squared times the derivative of y, which is the derivative of y. Isn't that nice how that works? All right, here, product rule. So derivative of x is 1. So 5y squared plus derivative of y squared, we get a 2 comes down. It's already a 5. So that'll be 10x y. And now y to the first times the derivative of y, which is y prime. All right, derivative of 3x, 3, because we're taking derivative with respect to x. And don't forget, you have to take the derivative of this side too. It doesn't say 10, you have to take the derivative of 10. The derivative of 10 is 0. All right, now, we don't need to know the derivative everywhere. We just need to know the derivative one-where. 1, 1. All right, so now, what do? Well, let's plug in. So we plug in x equals 1, y equals 1. And we get 6 times 1 times y prime plus 5 times 1 plus 10 times 1 times 1 times y prime. So that's 10 y prime plus 3 equals 0. All right. Well, that's 16y prime. Then 5 plus 3 can move to the other side. Negative 8, or y prime is negative 1/2. And that's our slope. Nice! We found our slope. Yeah, we've got our slope. Yeah, so let's put it together. So, point, slope. Y minus the y value, 1, is equal to our slope, minus 1/2. X minus our x value, 1. And that is a great answer. Or, if you like, you can say, look, this is y equals minus 1/2 x. And then you have to say, okay, so minus 1/2 times minus 1 makes plus 1/2. add 1 from the other side, and you get plus 3/2. And that's another way we could write the answer. Both are great. Both are lines. Not only are both lines, both are the tangent line to that curve at 1, 1. Woohoo! Nice! Find the derivative, that's what d dx means, the derivative of this. Ugh, that looks messy. The problem is we have a lot of stuff packed together. We don't like lots of things packed together. We don't mind lots of little things split apart, though. And so one of the things that we have to think about is there a way to pull things apart? And in particular, you might notice something here. So when we look at this, we have that e to the 3x. Okay, no problem. Downstairs, x tangent x. Great. Some of my best friends are x tangent x. But look here. You have that 2 plus cosine x raised to the power x squared plus 1. Now, what do you see there? X shows up downstairs and upstairs. So when a variable is both downstairs and upstairs, what does that tell us? The only chance we have is logarithmic differentiation. All right. Now, in general, if you see lots of stuff crammed together, logarithmic differentiation is a tool. But especially if you have function to a function, you have to pull out logarithmic differentiation. Now, logarithmic differentiation is a beautiful idea, and let's write down the generic formula for it. There's a couple of ways to think about it, by the way, and I will say differentiate. I can spell the word differentiation. There's a couple of ways to think about it, and oftentimes books will say, oh, set y equal this, take the... No. There's a simple formula, and here's how the formula works. Namely, suppose I want to find the derivative of a function f of x, where f of x, and we're going to go through some technical terms here, so where this is what's known as messy. And here I'm not talking about a soccer player, I'm just saying the expression, ugh, we don't want to deal with it. Terrible, terrible. Well, that's equal to f of x. Okay, that's good. We don't have to do anything with it. Times the derivative of natural log of f of x. You might say, well, you've made it worse. You put a log there. But here's the thing. Log has lots of wonderful properties. And one thing that happens is that when you take log, where there's lots of things of multiplication and division, you pull it apart. So here, this is, in some sense, it's acting like a splitter. You could say, oh, I'm taking my big problem and I'm turning it into lots of little problems, and I can handle little problems. All right, so with this in mind, we're ready to go. So we have that our derivative is, here's our f of x, so it's e to the 3x, 2 plus cosine x to the power x squared plus 1 over x tangent of x times the derivative of the natural log of e to the 3x, 2 plus cosine x to the power x squared plus 1, all over x tangent of x. Okay, now, what does log give us? Why did we do this? Why is it a splitter? So remember, we have three things. Multiplication becomes addition. Division becomes subtraction. And by the way, derivatives, we like addition, we like subtraction, because it says do each one separately. That's why we split it into small parts. And exponentiation, so log of a to the power b is b log a. So exponents come down. All right, so the first step in logarithmic differentiation, know the rule. The second step is not differentiation. The second step is use logs to pull things apart. So this will be equal to e to 3x, 2 plus cosine of x to the power x squared plus 1. And I'm going to add that the hardest part about this problem is not the problem, It's the writing. You're going to write a lot. Well, that's all right. So, again, we're not ready to take our derivative. Now, everything, we're thinking of splitting this into parts. So we get the stuff on the upstairs. We're going to think of it as stuff multiplying. So you have that e to the 3x is one part. That 2 plus cosine x to the power x squared plus 1 is another part. Downstairs x is a part. Tangent x is a part. So the upstairs parts add. Downstairs parts subtract. Okay, so here we go. This will be log e to the 3x plus log 2 plus cosine of x to the power x squared plus 1. Subtract log x, subtract log tangent of x. Okay, now, we've already made it look slightly better. We're going to do one quick thing, actually two quick things, but they're the same flavor. Namely, log of e to the 3x. The 3x can come down. Log of e is 1. So this whole term is 3x. Great. Here, exponent comes down. So this whole thing is x squared plus 1 log 2 plus cosine of x. Okay, and now we're ready. Okay, in fact, our next step is to write down the answer. So, recap. Know the formula for logarithmic differentiation. Use properties of logs to pull things apart. These are the properties of logs. And then take a derivative, and life is good. So e to the 3x, 2 plus cosine of x to the power x squared plus 1 over x tangent of x times derivative of 3x, 3. Here, product rule. Derivative of x squared plus 1, 2x. So 2x log 2 plus cosine of x plus first function x squared plus 1. And the derivative of log, you put the function on the inside downstairs, so 2 plus cosine x times the derivative of the function upstairs. Well, what's the derivative of 2 plus cosine x? It's negative sine of x. Derivative of log x, 1 over x. Derivative of tangent, well, okay, downstairs, tangent. Upstairs is derivative of tangent. Derivative of tangent, secant squared. And we're done. So the actual problem is not bad. Honestly, the hardest part is make sure you know the formula. Well, there's 3 hard parts. None of them are hard. Make sure you know the formula. Know the properties of logs. But the hardest part, I often think, and this is where I probably would lose points on this, is you have to write a lot. So there's lots of copying. So be careful with your copying. Don't lose easy points. Lose hard points, right? But just take your time. You can do it. You're great. Given h of x is 2 log of 1 plus 4x squared and 3 arctangent 2x, find all x where h double prime of x equals 0. All right, so this is a problem so nice, we're going to do the derivative twice. So let's start. So we need to know our logs and our arctangent derivative. So let's start there. So first derivative, h prime of x. We have the 2. Whenever you're taking the derivative of a log, it's a fraction. Downstairs is the function. Upstairs is the derivative. Well, the derivative of 1 plus 4x squared, 8x plus 3. Now for arctangent, it's 1 over 1 plus something squared. Now what goes here is the inside. So 2x times, chain rule, the derivative of the inside, derivative of 2x is 2. All right, so there we go. That's good. Now we're going to take another derivative, and my sort of philosophy is if you're going to do something, clean it up and make it simple first. So let's make some quick notes. 2x squared is 4x squared. So these actually have the same denominator. So great, let's put it as one fraction. Upstairs we have 16x, and 3 times 2 makes 6. Downstairs, 1 plus 4x squared. All right, so first derivative done, in the bag. Time for derivative number 2. All right, so we have h double prime of x, and what's our rule? Now we have a fraction, quotient rule. So let's work through that. The bottom, or some people like to say low, to the top, d high, so that's 16, minus high, the top, d low, to the bottom, derivative of 1 plus 4x squared, 8x, divided by the bottom term squared. Okay, let's work on the top. Okay, so we'll distribute here. So we have 16, and 16 times 4 is 64. Now, the 8 and the minus, don't forget the minus. 8 times 16, it's a number. It's 128, right? Oh yeah, powers of 2, right? Who doesn't love a good power of 2? A nice power of 2 in the morning. So 128x squared minus, and then 6 times 8x, and don't forget that minus. It's easy to forget the minus. They might say, how do you know that? Because I've done it before. So that's why I try to pay extra attention. All right, so 6, 8, minus 48x. And, okay, all that over the bottom squared. We're getting close. Let's group 64x squared minus 128x squared. That's negative 64x squared minus 48x. Great. Plus 16. And all of that over 1 plus 4x squared. And last thing to simplify, the coefficients, 16, 48, 64, they all have something in common. They're all multiples of 16. And let's pull out negative, because I like to have the coefficient of x squared be a positive coefficient. So negative 16 times 4x squared plus 3x, because we're putting on a negative, and then minus 1. All right, so here's our second derivative. Now, what are we doing? We're setting our second derivative equal to 0, because it tells us we want the second derivative equal to 0. Say, okay, so we set it equal to 0. Now, what part would make it 0? Well, it's this part. It's the upstairs part. So we say, oh, okay, now that's not too bad. What that's telling us is it says, hey, we have reduced our problem to saying, when does 4x squared plus 3x minus 1 equal 0? Great. That's a quadratic. We see these all the time. We have tools. And so now we're like, okay, we could factor, because our teachers are probably nice and probably will factor. Or maybe we're not seeing it right away. And that's okay if we don't see it right away, because we have tools, and we can use our tools. So what tools do we have? Well, the quadratic formula. Say, all right, let's pull out the quadratic formula. So x equals negative b, so negative 3 plus minus square root b squared 9 minus 4ac. Well, 4 and negative 1 times negative 4 makes a plus 16 all over 2a. All right, well, that's negative 3 plus or minus. Square root of 25 is 8. Square root of 25 is 5. Got ahead of myself. Over 8. And so we get negative 3 plus 5 over 8. And negative 3 minus 5 over 8. Well, negative 3 plus 5 is 2. 2 over 8 is 1/4. Negative 3 minus 5 is negative 8. Divided by 8 makes negative 1. And so our two answers, 1/4 and negative 1. Nice. All right. Woohoo! suppose that the following equation defines y as a differentiable function of x. So we have 2x plus 3e to the y equals x squared plus y. Now, notice something. This is not y as a function of x. Y's and x's are being mixed together. And so it's not going to be really clean necessarily. So when we're looking at this, we're thinking, oh, this is going to be an implicit function. All right, well, that's okay. We have tools for implicit functions. And now it says, find the value of d squared y dx squared at the point 3, 0. Now remember, when we think implicit function, we really have this sort of thought, namely that y is a function of x. So let's start by finding our first derivative. So here we go. We'll start with our 2x plus 3e to the y equals x squared plus y. And now, first step, derivative number 1. So we're going to take d dx. Derivative of 2x with respect to x, 2. Derivative of 3ey with respect to x. So remember, y is a function of x. Got to pull out the chain rule. So we'll have 3. Derivative of e to something is e to that something times the derivative of that something, which is y prime. All right, derivative of x squared. Well, that's 2x. Derivative of y is y prime. Okay, great. Now, but what do we want? We want second derivative. All right, no worries. So let's do another derivative. What? A second one right away? Yeah, let's do this. Oh. All right. So again, take derivative with respect to x. We're going to have derivative of 2, 0. Here, product rule. So let's unwrap this slowly. We have two pieces. The derivative of the first piece, well, that would be 3e to the y, chain rule, derivative of y, y prime, times the second piece, y prime. And then plus the first piece, 3e to the y, times the derivative of the second piece, derivative of y prime, y double prime, equals derivative of 2x with respect to x, 2. Derivative of y prime with respect to x is y double prime. And I might say, wait, why is the derivative of y prime y double prime? Well, you see this thought bubble? It's a similar thought bubble that says, oh, y prime is also a function of x. Okay, now what do we do? Well, this gives our second derivative, kind of. It also involves the first derivative, but, whatever. We'll figure that out. But we have y double primes. Cool. So what do we need to do? Well, we need to plug in the point 3, 0. Okay, so now we're going to evaluate. All right, so here we go. We're going to plug in x equals 3, y equals 0. And we start. We have 3e to the 0 times y prime. Wait, what? What's y prime? Oh, well, actually for that, let's come back up here. We'll plug in x equals 3, y equals 0. And what do we see? We get 2 plus 3e to the 0, y prime is equal to 2 times 3 plus y prime. All right. Well, we can rearrange, right? We have 3y prime there, so that becomes 2y prime. And then here, subtract 2. 6 minus 2 is 4, or y prime equals 2. Okay, so that y prime is 2. So that says, hey, this y prime is 2 times 2 plus 3e to the 0 times y double prime, which is what we're trying to solve for, is equal to 2 plus y double prime. All right? So we're almost there. Let's clean this up. We have 12 plus 3y double prime equals 2 plus y double prime, or subtract 2, subtract 3y double prime. We could say 10 is negative 2y double prime, or y double prime is negative 5. There we go. So the second derivative is negative 5. Now, this might seem like, wait, it feels like we cheated. It seems like it may be a little bit too easy, or maybe it seems like it's a little bit too weird. Recap. Start with the implicit function, take the derivative. And it gives you another implicit relationship that now involves an additional term, namely the y prime. And so you could solve for y prime as a fraction, but that means you have to take derivative of a fraction. I'm not a big fan. So I say don't do that. Just say, look, go straight ahead and take your next derivative. Now, we're going to evaluate, because we will need y prime, so that's why we plug in and we work through and say, okay, what's going on? And oh, wait a second. Did I get this right? Yeah. Okay, good. I was worried about the sign. Yeah. Yep. And now, what do we have? Well, take the second derivative. Be super careful. The second derivative is where people make mistakes, because they remember, oh, y is a function of x, but y prime is also a function of x. So you got to really work it through. But again, plug in, and plug in for x, for y, and for y prime using the first part. Simplify, solve, life is good. Nice. Nice. Let f of x be a differentiable function that has an inverse f inverse of x. The line y equals 2/7 x plus 3/7 is tangent to the graph of y equals f of x at the point where x equals f inverse of 3. Find the equation of the line tangent to the graph of f inverse of x at x equals 3. All right, now we got to start unraveling this, our information we want, right? So let's talk about what we have. Now we have a tangent line. We say, okay, cool beans. And that's our y equals 2/7 x plus 3/7. And we say, okay, what does our tangent line have? It has two pieces of information, slope, point. So let's talk about slope. That's the derivative. So slope, which equals f prime of something, and that's equal to 2/7. I'm being very vague here about what that f prime of something is. And now our point, well, that says f of something equals something. Now, the tempting thing is to say, oh, 3, right? So we're doing our tangent line is at x equals 3. It's not. They're being tricky. Notice here, let's parse this. X is equal to f inverse of 3. So f of x equals 3. So this part right here, this is your y value. So what's our x value? Now, you might say we can't figure it out, but we can, because we have our line. So we say, look, if I know the y value, I can solve. So we have 3 equals 2/7 x plus 3/7. Okay, multiply by 7. 21 equals 2x plus 3. 18, so I subtract 3 equals 2x. X equals 9. So the tangent line is occurring at x equals 9, y equals 3. And then we have f prime of 9. All right, so we've done a lot of the hard work. That 9 is going to be important to us. Now, what's our goal? We're trying to find the graph of f inverse of x at x equals 3. So notice that the point, this 3, 9 here, sorry, excuse me, got ahead of myself. This is 9, 3. This is a point on the graph y equals f of x. So the point 3, 9, that's the point of y equals f inverse of x, because you swap x and y. So here, this is a point on our tangent line. So good news us. So that's one piece of information. Now the other piece of information that we need is our slope. All right? Where do we get that? Well, we have this information. So notice if I take the derivative of f inverse of x, that's 1 over f prime of f inverse of x. So at x equals 3, we get 1 over f prime of f inverse of 3. But we actually know what f inverse of 3 is. It's 9. So it's 1 over f prime of 9, which is just a fancy way of saying it's 1 over that part. So we end up with 7 halves. You flip it over. So here's our slope. All right, we have our point and we have our slope. We put them together. So y minus 9 is equal to 7 halves, x minus 3. And there's our answer. We can rearrange, and I don't know if it would make me much nicer, so I'm happy with that. Life is good. So what's the key idea here? It's not actually doing a lot of math, it's just understanding what things represent. The most subtle part is to recognize, oh, if I have x as f inverse of 3, that tells me my y value, and I can use this to figure out the corresponding x value. So it's sort of flipping the script, right? It's not they gave us x and we found y, they gave us y and we had to find x. Other than that, life was pretty good. And all right. Woohoo! An implicit function has a vertical, straight up and down, tangent line, if dx dy equals 0. So dy dx equals 0 says, oh, there's no change in y as we change x. So that's why it's horizontal. Move x along, y doesn't change. Dx dy equals 0 means there's no change in x if we change y. So you're going straight up and down. So that's, okay, all right, seems reasonable. Find the 4. So, okay, so we better find 4 points on the implicitly defined function 2y cubed minus 9y squared equals x squared minus 8x minus 20, where we have a vertical tangent line. All right, so what's the idea? Well, notice there's sort of a key thing. We see there's this part derivative here, but it's dx dy. So what does that mean? Well, now it says, hey, we've got to change our thinking. It's still going to be implicit, but now instead of thinking of y as a function of x, we're going to think of x as a function of y. Can we do that? Absolutely. That's the thing about implicit. We can flip roles. Life is fine. So we'll start with 2y cubed minus 9y squared equals x squared minus 8x minus 20. And we're going to take the derivative with respect to y. All right, derivative of 2y cubed, 6y squared. Derivative of 9y squared, 18y. Derivative of 2x, well, remember, we're taking derivative with respect to y. X is a function of y. So it's 2x times dx dy. minus 8, derivative of x with respect to y, derivative of x with respect to y, and derivative of 20, 0. Now, what are we after? We are after the points where dx dy is equal to 0. How do we know that? Because it tells us that. Say, okay, well, so we want to put dx dy to be 0. And so that tells us, oh, this will happen when 6y squared minus 18y is equal to 0, because that just goes away. Well, that's okay. What does that say? Factor out 6y times y minus 3 equals 0. So we end up with two possibilities. Either where y equals 0 or where y equals 3. Now, we've done the parts with differentiation. We need to find the points on the curve. We now have the y values. We need to find the x values. So let's start. We have the y equals 0. So we're on our curve. Plug in y equals 0. We get 0, 0 equals x squared minus 8x minus 20. Well, does that factor? You can think of two numbers that multiply to give negative 20, but would add to give negative 8. I think I can think of two numbers that do that. That would be what? Minus 10 and plus 2. Let's check. X squared, good. 2x minus 10x is negative 8x. Ah, nice. Good one, Steve. Well, thank you, Steve. You're awesome. We're all awesome. Okay. Negative 10 times 2, negative 20. So that says, oh, okay, that says, hey, cool, x equals 10 or x equals negative 2. Now remember, that combines with y equals 0. So that says we have a point 10, 0, and a point negative 2, 0. Okay, so here are two of our points. But that's only half the story, because we also have another half. What happens if y equals 3? Well, 2 times 3 cubed is 54, right? 3 cubed is 27. And 9 times 3 squared, 81, is equal to x squared minus 8x minus 20. All right, well, let's move these across. Now, 54 minus 81, that's negative 27. So when you move it across, it'll be a plus 27. Okay? That's good. So negative 20 plus 27 would give us what? It would give us a plus 7. Okay, so now we're looking for two numbers that multiply together to give 7 and add to give negative 8. I think I know two numbers. In fact, 7 is really hard to factor, or super easy to factor, depending upon your perspective. So factors, and let's check. X squared minus 7x minus x is minus 8x and plus 7. So this says, oh, either x equals 1 or x equals 7. Combine with y equals 3, so we get the point 1 comma 3 and the point 7 comma 3. And there are our other 2 points. 1, 2, 3, 4. 4 points. 4 points where we have a nice vertical tangent line. Cool. Nice. Given the implicit curve, arctangent of x plus y squared equals 3e to the x plus 2y plus xy plus 5. Find the tangent line at the point negative 4 comma 2. All right. So, key word here, implicit. We've seen that word a lot today. So what do we know? Well, we know we're doing implicit differentiation. We also see that we're doing a tangent line. So we say, hey, what do we need? We need a point. Good news. We have our point. And we need a slope. And so slope means derivative. And as always, because we're doing implicit differentiation, we say, just remember y is a function of x and take the derivative. So here we go. Arctangent x plus y squared equals 3e e to the x plus 2y plus xy plus 5. And I'm just copying it down. Now the derivative. We're taking the derivative of both sides with respect to x. That gives us dy dx, y prime, that's our slope. So, d dx, be 1 over 1 plus something squared. That something is what's on the inside of our tangent. X plus y squared squared times the derivative of the inside. Derivative of x is 1. Derivative of y squared, remembering that y is a function of x, 2y, y prime. Great. Equals, here, 3, and then e to something is e to that something times the derivative of that something. So the derivative of x is 1, and then the derivative of y is the derivative of y. I put y prime. And now product rule, x times y. Well, it'll be the first times the derivative of the second plus the derivative of the first times the second plus the first times the derivative of the second. There we go. And derivative of y, y prime, and the derivative of 5 is 0. We don't need to rearrange because we're not after y prime as a function of x and y. What are we after? We're after y prime at a point. So what should we do? Plug it in. So evaluate. And I always find it's simpler to evaluate and then rearrange than it is to rearrange and then evaluate. Now, we have 1 over 1 plus negative 4 plus 4, well, that's 0, squared, 0, cool. Then 1 plus 2y, well, y is 2, so that would be 4 y prime, right? 2 times 2 times y prime. We don't know y prime, that's what we're solving for, so it's okay that we have a y prime. Equals 3e. Now x plus 2i, negative 4 plus 4 is 0. Oh, wow. They chose nice numbers. They care about us. They really do. They really care. Math teachers are the best. Oh. All right, 1 plus 2y prime, great, plus y is 2, and x is minus 4. Okay, so let's clean up here. Okay, and so we have 1 plus 4y prime equals 3 distributes 3 plus 6y prime plus 2 minus 4y prime. And, well, okay, let's move all the y primes over. So this will become 8y prime minus 6y prime, that's 2y prime. Here we have 3 plus 2 is 5. And then subtract 1, that would be 4. Or y prime equals 2. That's our slope. Now, we're not done, but we've done all the hard work. The only thing left for us to do is to actually write down the answer. That's the best part. It's our favorite part, right? Because we were asked to find the tangent line. But we have our point, we have our slope. So, y minus our y value is equal to 2, which is our slope, x minus our x value. And there we go. There's our answer. Or if we wanted to, we would say, oh, that's the same as y equals 2x. Now here you'll see we have a plus 4, and then times by 2 makes a plus 8 and plus 10. So y equals 2x plus 10. And there's our tangent line. All right. Nice. Woohoo. Yeah. Let y equal 12x times the square root of x squared minus 7 divided by x plus 4 to the power 1/3. Use logarithmic differentiation to find dy dx at x equals 4. Now, what tool should we be using? I think, hear me out, logarithmic differentiation. Now, why do I think that? Because they tell us. Yeah, that's a pretty good reason. very compelling. Okay, so before we get too far, let's just make a quick note. Let's make this algebra friendly, or I should say calculus friendly, right? This square root, that's the same as x squared minus 7 to the 1/2. And the reason I say that's calculus friendly is because our rule is phrased in terms of things to a number. Okay, so logarithmic differentiation, we know the rule. So that says, hey, if I want to find f prime of x, that's equal to f of x times the derivative of the natural log of f of x. All right, so we're going to go through and figure this out. So in particular, we have that dy dx is the same function, which is 12x x squared minus 7 to the 1/2 divided by x plus 4 to the 1/3 times the derivative of the natural log of 12x x squared minus 7 to the 1/2 divided by x plus 4 to the 1/3. Now, remember, we have rules. So log of AB, that's log A plus log B. Log of A over B, log A minus log B, and log of A to the B is B log A. All right, that's our pull things apart with log tools. All right, well, isn't that very convenient? Almost as if we planned it, right? Well, no, of course, we didn't plan it. That's our idea. So we have 12x x squared minus 7 to the 1/2 x plus 4 to the 1/3 times the derivative. Now, we're going to do this in one step for the logs. So everything that's getting multiplied upstairs, it gets added. So log 12 plus log x plus log of x squared minus 7 to the 1/2. I'm going to automatically put that rule in. So 1/2 log x squared minus 7. Downstairs, subtract. So minus, and notice the 1/3 exponent is going to come down. 1/3 log x plus 4. All right, so we took our definition, we used our logs to pull things apart, and now we take our derivative. Okay, so what do we get? Well, derivative of a constant, because log 12 is a constant, 0. Derivative of 1 over x, derivative of log x. Got ahead of myself. 1 over x plus 1/2. Derivative of log of x squared minus 7. Well, x squared minus 7 goes downstairs. Derivative of 2x goes upstairs. Minus 1/3. Derivative of log x plus 4. X plus 4 goes downstairs. Derivative of x plus 4 goes upstairs. Okay, now we took the derivative using logarithmic differentiation. What do we need to do? We need to plug in 4. Why do we need to plug in 4? Because it tells us. Good reason. So we plug in at x equals 4. We have in the front 12 times 4 times 16 minus 7 is 9 to the 1/2. Downstairs we have 4 plus 4 is 8 to the 1/3. Okay, we'll clean that up. Times 1 over 4 plus, now here we'll have 4 squared, and 7 years ago, wait, no, sorry, that's something else. 4 squared is 16. 16 minus 7 is 9. 4 over 9. And minus, here we'll have a 1. And, okay, 4 plus 4 is 8 times 3 is 24. Now, things should clean up. I mean, I would hope they do. 8 to the 1/3 cubed root of 8, that's 2. So here's a 2. Oh, I have lots of 2's upstairs, so let's put a 2 there. 9 to the 1/2, that's a 3. So we really have 72. Okay, so 12 times 2 times 3, that's 72. So this is the same as 72 over 4 plus 4 times 72 over 9 minus 72 over 24. Now, if things are nice, and people are nice, mathematicians are nice, beautiful things should happen. 72 divided by 4 is 18. 72 divided by 9, 8. 8 times 4, 32. 72 divided by 24, 3. Minus. 18 plus 32 is 50. 50 subtract 3 is 47. There we go. It's 47. A nice whole number. Yes, math is, after all, very wholesome, right? That's all right. I'll be here all semester. The slope of the tangent line to the graph of y equals arctangent log of bx at x equals e squared is 1 over 17 e to the minus 2. Find all possible values of the constant b. All right. Well, let's just work through it. So we have slope of the tangent line, which is just a fancy way of saying the derivative. So the derivative at x equals e squared is 1 over 17 e to the minus 2. So let's start by taking some derivatives. So we have y equals arctangent log of bx. Now notice this is log of b times x. So I can write this as log b plus log x. I can separate it in that way. So now take a derivative, and let's see what happens. We'll have y prime. So for arctangent, it's 1 over 1 plus the inside, log b plus log x squared, times the derivative of the inside. Well, derivative of log b is 0 because it's a constant, and derivative of log x is 1 over x. All right, so now we know what the derivative looks like. And we say, okay, well, what's happening? At x equals e squared, we get the following. 1 over 1 plus log b. Log of e squared. Log of e squared is 2, right? Why? Log of e squared is the same as 2 log of e, because the 2 comes down. But log of e is 1, and so it's 2. All right, so 1 over log b plus 2 quantity squared times 1 over e squared is equal to, right, that's the is, 1 over 17. Now notice e to the minus 2 is just a fancy way of saying 1 over e squared. Flip both sides. Log of b plus 2 squared, and then there's a plus 1, better be 17. Or log of b plus 2 squared has to be 16. All right, we're almost there. Log of b plus 2, take the square root, is plus or minus 4, right? Because you got to account for both possibilities. So that says, hey, either log of b is 4 subtract 2, 2, or log of b is minus 4 subtract 2, which is negative 6. All right, well that says if log of b equals 2, to get b out of the log, you do what? Exponentiation. So e to log b is e to the e squared, e to log b, e to the negative 6. So we get b equals e squared. b equals e to negative 6. And those are our two possibilities. And there we go. You did it. Woohoo! Yeah! Let f of x be an invertible function whose inverse is twice differentiable. Use the values given below to find the second derivative of f inverse at 3. Interesting. All right. Well, let's figure this out. So we need to find the second derivative of f inverse. So how do we do that? Well, let's start. We have f inverse of x. Oops. F inverse, I can write f inverse. There we go. Take one derivative. And what do you have? Well, the rule, there's a nice rule for this, 1 over f prime of f inverse of x. Okay, there's our formula for inverse. Now, take another derivative. Well, notice this can be written as f prime, f inverse of x to the minus 1 power. So, when we take another derivative, that's our second derivative, right? We've taken two derivatives, that's what we're after. So we're going to have the following. We'll have a minus 1 comes down, f prime, f inverse of x to the minus 2 times the derivative of the inside. Now, here, what's our next layer? So our next layer, we're working our way in. So we've taken the outside part. Now we're into the next layer. It's the f prime of f inverse of x. So that derivative would be f double prime of f inverse of x times the derivative of the inside. All right, so got to keep working our way through. It's layers, right? Lots and lots of layers. The derivative of f inverse of x is 1 over f prime, that's a prime, f inverse of x. Okay, so let's see, what do we have when we put it all together? Now, these terms actually are the same. F prime, f inverse of x. This is downstairs. This is also downstairs. There's two of them. So those will combine together. So upstairs we have a minus f double prime, f inverse of x over f prime, f inverse of x cubed, right? 2 and 1. All right, so there's the formula for the second derivative. Whew! Okay, now, with this in mind, what do we do? Well, we plug in. We plug in 3. So, we say, well, look, we want minus f double prime of f inverse of 3 divide by f prime of f inverse of 3 cubed. Now, how do we find f inverse of 3? To find f inverse of 3, well, f inverse of 3 equals what? Well, that's the same as saying f of the thing we want is 3. So we're looking for, when does f of something equal 3? All right, we scan, here's f, and we want the output to be 3, not the input, the output. So we say, f of something equals 3 happens here. So the conclusion is that f inverse of 3 is 4. Okay? So minus f double prime of 4 divided by f prime of 4 cubed. Okay? Now, f double prime of 4, 40. So minus 40. F prime of 4, 2. 2 cubed. All right, well, 40 divided by 8 is negative 5. There we go. And so, if you look at it, what did we use? Well, we used this information to figure out f inverse is 4, and then we use that information. And I say, well, wait, why did they give us all of that? It was a red herring, right? They'll give you some information. You may not use all of it, because part of it is saying, do you know what information you're supposed to be using? And if you don't, that means you haven't mastered the tool. And so there we go. We did it. We made it. Woohoo! Yay! Keep at it. You're amazing.